Welcome back. So today we are going to learn about moment of inertia in our present video. Okay. So I guess everyone might have heard about a word called inertia. One or the other time probably you might have heard about this. So what do you mean by inertia? So mostly we will come across this inertia in translatory motion. Probably you might have learned initially on this only. So, in translatory motion, when we will learn this inertia, we learn it as a property of a body, or we can say property of a rigid body, we can say. Correct. And what kind of that property is? So, it is to resist. What? It is to resist its state of motion. Sir, what is state of motion, sir? So, state of motion means either if it was initially at rest, so it will have a tendency that it doesn't want to get into motion, and if it was initially in uniform motion, it doesn't want to come back to at rest. So, such a tendency where it resists towards to change its state of motion, and such a property we call it as inertia. That is we have seen in translatory motion, correct? And also we know that mass of the body is a pure measure of inertia. So this one we clearly know about this, and we already had learned previously now. So why did you bring this over here, sir? Now exactly. So how a rigid body in translatory motion has a property to resist in change its state of motion. Similarly, in rotational motion or rotatory motion also you can consider. Okay na? Similarly, in rotational motion, similarly in rotational motion, as of like in translatory motion, the object here also the rigid body also by virtue, okay na, the property by virtue as usual, same like inertia how you can say, okay na, property by virtue. And what is this? Which opposes any change in its state of motion, any change in its state of motion. Sir, here what are the state of motion, sir, in this case? In rotational motion. So if in that case, if you want to understand it clearly, here also as usual the case same, that is first one is rest, and the second one is, guess what it could be? Uniform circular motion. There it is uniform motion in translatory, here in rotational uniform circular motion. Thus this property by which in rotational motion a rigid body opposes any change in its state of motion, either rest or uniform circular motion, we call this one as rotational inertia. We call this property as rotational inertia, and thus we need someone to measure this rotational inertia. Likewise in mass in translatory motion, so here who will measure, and the word or that entity we call it as moment of inertia. That's it, simple words. Moment of inertia is measure of rotational inertia. That's it. There ends your discussion about moment of inertia. So what does now this moment of inertia states? It is a measure of rotational inertia, that is property by virtue which opposes any change in its state of motion of rest or uniform circular motion. That's it. This is your moment of inertia. Thus what I can say directly, moment of inertia is rotational analog. See here, very beautifully explained that moment of inertia is rotational analog. So rotational analog means similarity, we can say. So rotational analog to inertia in translatory motion. That's it. Easy to understand what is a moment of inertia. That's it. So to explain this one in detail, analog to mass in rotational motion, that's what we are saying, that so moment of inertia is nothing but inertia, whatever we call this one, what you say, like rotational analog, where we are considering this as measure of rotational inertia, right? So what I can say this one here, analog to, directly I can say mass. So let us prove this one with some basic entities, whatever we can measure in rotational motion, that is with the help of, I can say, kinetic energy. A basic explanation I can do, kinetic energy, and that is Ke. So let me suppose there are n number of particles in a rigid body. So I would like to draw you a rigid body. So some basic shaped like this rigid body I just considered, and say there is also an axis of rotation for us in this way, and there are n number of particles, m1, m2, m3, likewise n number of particles situated in this rigid body, and say from each rigid body the distance of this axis of rotation be considered as r1 over here, and this is m1, let me suppose, and similarly here m2, and the distance be r2. Similarly there are n number of particles I said, so therefore this is mn, and say the distance be rn, and what is this, I called it as axis of rotation about which the rigid body is going to rotate. So in that case now every particle will undergo a circular path only. So in such a case, in that circular path, obviously every particle will have its own velocity, and that to that velocity will be in the tangential path. See, I can show you this one. It will be in a circular path in this kind. So when a particle is undergoing such a circular path at some particular position, it might have its velocity, right? So based on that, if I can write its kinetic energy, so let me suppose it is rotating in this direction. So therefore the kinetic energy is given by half mv square, half mv square. So therefore similarly for first mass, say it is given by k1, that is half m1 v1 square. Since it is a rigid body and it is under rotatory motion, all the particles will have a constant angular velocity omega. So thus I can relate linear velocity and angular velocity by v is equals to r omega, and thus replacing all these terms I'll get k1 is equal to half m1 r1 square omega square, since omega is constant for every particle in the circular motion, or whatever you call this as rotatory motion. And now this is for one particle. Similarly there are n number of particles, right? So therefore total kinetic energy of the motion of the rigid body is given by k1 plus k2 plus so on plus kn. So I can write this one as half m1 r1 square omega square plus half m2 r2 square omega square plus so on plus half mn rn square omega square. So what I can take directly common here, half omega square I can take common. So therefore it will be m1 r1 square plus m2 r2 square plus so on plus mn rn square. So let me replace this one by summation so that easily you all can understand, into summation I is equals to 1 to n mi ri square, and this one whatever the term we have written now, summation mi ri square is nothing but your moment of inertia. So half into I into omega square. See here it is similar to ke is equal to half mv square, where v is linear velocity, omega is angular velocity, half and half vary, so I and m are analog to each other. So therefore moment of inertia is equal to summation of I is equal to 1 to n mi ri square. So this is your moment of inertia of system of particles, or you can say if n number of masses present or smaller particles present in a rigid body, then sum of all those we will give it as a moment of inertia I. So directly from this equation I can clearly say that moment of inertia is analogous to mass. Clear? So therefore moment of inertia is rotational analog. Moment of inertia is rotational analog to mass in translatory motion. So I hope everyone understood about moment of inertia. So in our next video we will try calculating the moment of inertia for various types of regular figures clearly. But before that, let us have a small change in this formula so that it will be easy for you to measure or calculate the moment of inertia. So therefore I is equal to summation I would like to replace by integral and integral of smaller masses, right? So therefore dm into r square. So integral dm r square is going to give you the some moment of inertia of the total rigid body, and also you can say mass is nothing but your volume into density. So therefore I can even write I is equals to integral r square rho into dv, where rho is your density and dv is your small change in the volume, I can say clearly. So therefore thus moment of inertia can be calculated using either of these bodies for continuous mass distributions. Okay, so thus moment of inertia will be calculated using either of these formulae, and from our next video we will be calculating the moment of inertia for various regular figures like uniform rod, ring, disc, etc. Okay, hope you all understood this. Have a great day. Bye bye.